Okay, go. Hello everybody, welcome to the second of our series of CPS seminars this term. And as we know, we're going through some of our recent appointments and promotions for our speakers this term. And so I'm very pleased to welcome Louise Hirst. Louise joined us in 2018 as a joint appointment with the Department of Materials Science and Metallurgy. And she works in exotic forms of 3-5 photovoltaics and applications for space and other challenging environments, very different from the conventional large area solar power for the power grid. She came to us from the US Naval Research Laboratory, where she was a staff scientist, and before that she was at Imperial College London as a postdoc. She's facing a challenging situation, being one of the first people to attempt to do a joint lectureship in on the West Cambridge site. But from all the evidence I've seen, she's making a great success of it and making links across the place in a way which is really very nice to see. So without further ado, I will pass over to Louise to introduce her talk on space photovoltaic challenges fundamental to applied. Thank you. Oh, sorry, one last thing. The last Q&A session was difficult for people to type in the answers, so Leona is going to circulate a live Q&A session at the end of this one on a separate link, so people can join as a normal video conference and will be able to ask their questions in person rather than somebody reading them out from a text feed. So please make sure that you save your questions up and ask them as normal at the end in the separate session, which you will have to move to. Thank you. Sorry, over to Louise now.
Okay, hello everyone. Can you hear and see me and hopefully see my slides as well?
I can't answer. Nobody can answer.
Nobody can answer, but you can, Andy. Okay, perfect. All right, well, I'll get started then. Thanks very much for that introduction, and also thank you to the organisers for putting together this whole lecture series. I think it's a really great mechanism for us to try and connect as a department. Many of us will have had that experience of perhaps attending an international conference and going halfway around the world only to discover that some of the best interactions we have might be with someone that we work with just down the corridor, but we just didn't realise we had a research connection. So hopefully this lecture series can be a great forum for creating those types of connections. So today I'm going to talk about space photovoltaic challenges. When I'm saying fundamental to applied, what I'm really talking about here is a pipeline. Here we go. Sorry, I'm not quite sure if I'm able to operate these slides quite correctly, but hopefully you can see the change of slide there. Or Leona, are the slides changing? I actually can't quite see.
Yes, they are. You're on space power technology pipeline.
Okay, perfect. Thank you. So what we're talking about here is a technology pipeline. And to describe what that really looks like, I'm actually going to start at the output end here. So looking at the things that we'd really like to be able to do with our space power systems and the things that we might be able to actually enable. So one of the key targets is next generation satellite networks. So there is ever increasing demand for space-based services, and we need new power systems to allow that to happen. The other area that is, of course, extremely interesting, particularly probably for a physics department, is space exploration and the potential for space science experiments. What do we need from our technology platform, from our power systems to make that possible? Particularly bearing in mind that many of the things we'd like to do, that we'd like to explore, may be taking place in quite hostile environments. So when we talk about space power, really we mean space photovoltaics. That's the abundant source that is available to us. What would we like from these systems? What would we like to be able to do? Well, that's kind of this first section here of the inputs. So we're interested in being able to try out new form factors. So the current form factor of having a centralized payload that has these rigid satellite wings, that design has existed for decades now, and really it's limited by the PV array itself and the rigid nature of the PV array. If we could design that in a different way, we could potentially enable roll-up form factors that are really great for stowage for launch, or potentially conformal type geometries where we have a coating of photovoltaics over a curved surface. We can really unconstrain ourselves in terms of satellite design. So that's something we'd like to be able to do. Another key thing is costs. For many decades, we've somewhat thought of space technologies themselves as being somewhat immune to cost, because there's such a heavy cost burden with the cost of launch already, that really the cost of the technology itself is minimal. But that's changing, right? We're entering a new era where space technology, space services are provided commercially, and actually the cost of launch is coming down a lot. And so we need to be mindful of actually the cost of the technology that we're putting on board there. Next up is mass. Mass is important for two reasons. One, because it links in with cost. So it costs between around $5,000 and $30,000 per kilogram to launch a satellite. And so we need to obviously be keeping that mass down as low as possible for cost reasons. But also there's a fundamental limit to how much we can launch with the launch platforms that we have available. So we obviously can't exceed that. So keeping low mass for our power system is really important. It makes space then for extra things that we might like from a payload. Next up is efficiency. So that's the efficiency of solar energy conversion within the power system itself. Space PV systems are high efficiency systems generally. This feeds into cost, of course, but it may also be important because we might have a limited area that we're working with. So we need a certain amount of power for our payload, and we only have a certain amount of stowage volume, and so we want the most efficient cells really operating. Now, all of these things are things that we might like potentially for terrestrial applications, particularly remote terrestrial applications. But one of the really unique factors for space applications is radiation tolerance. This is a really limiting factor in terms of the types of missions that we can do and the lifetime of the technology. And in fact, overwhelmingly, our beginning of life performance is less important than our end of life performance. That's what really limits what we can put on a satellite, what kind of payloads we can power. So that's kind of our wish list, but we need to have some more fundamental inputs in order to address this wish list. One of those things is looking at new types of device architecture. One of our big development pushes here is to move towards ultra-thin geometries, allowing us to actually address many of these different factors. But part of that, the push towards ultra-thin, is better light management systems and integration of nanophotonic structures. Further back in the pipeline, we also need to be mindful of how are we actually fabricating the materials that we are using. Are there ways that we could do it more cheaply, more efficiently? Are we happy with the alloys that we have? Would we like to adapt them to different types of alloys, or even use the same family of alloys, but perhaps drive them into new regimes where we can get more efficient power conversion? So this is the story that we're really working on in terms of research. What we are not doing, this might seem like a slightly odd slide, I guess, to have in such an early stage of a talk, but I think it's really important to have an abundance of clarity on this particular point. While many of the things that I've discussed do have relevance to terrestrial applications, we are really not trying to compete with flat plate silicon for domestic and utility scale power generation. So in the last decade, we've seen a real plummeting of the cost of silicon. We can see that in this chart of dollars per watt value for residential PV installs. And this little bottom slice here actually refers to the price of the module. Silicon is now so cheap that it's really cost competitive. It's, on a par with other construction materials like steel, for example. So it really is fantastically cheap. But being cheap is not everything. It's also pretty good. It's very efficient, and it's also highly reliable. We know how it performs in the field over many decades, and that demonstrated performance is bankable. So it's a technology that people like to invest in. So you can see what's happened with 3.5 technologies for concentrated photovoltaics over the last decade compared to flat plate silicon. They're actually pretty comparable in terms of cost. And in the early 2010s, we saw a big increase in concentrated photovoltaics being installed in areas like the south of Spain. But actually, that's really tailed off with the crash in the price of silicon. It's not simply enough to be cost competitive with silicon. Being also reliable and low risk is fantastically important in this environment. And when we consider that actually this is a technology that's going to be addressing climate change, and that is happening now and in the next 10 years, really there is only one credible option to meaningfully address that, and that is silicon. So that's why I always put this slide in, to make it really clear that we're not competing with silicon. Silicon is the technology that's going to address climate change for domestic and utility scale power generation. That said, is there a role for space technologies in climate change? And the answer to that is most certainly yes. We have, and that is through the provision of space-based services. So space technologies are completely ubiquitous already within our daily lives. So providing communications and navigation and real-time imaging, for example. How do they connect with things like climate change? Well, the data that we receive from our space-based services allows for the much more efficient connection with energy networks. So allowing us to use meteorological data, for example, to make sure our grids are operating in an efficient way. Also, the efficient use of agriculture, the efficient use of land. Climate monitoring as well. Obviously, a huge amount of the data that we need to understand climate change and therefore mitigate climate change is associated with the data that we receive from our space-based services. Also, the linking up of transport networks, right? So logistics and allowing us to really engage globally and not be restricted, but do so in a way that's very energy efficient. There's also other ways in which, of course, we use space-based services. Our emergency services are really dependent on them, not just domestically, but if we think about the types of emergency services that are required around natural disasters, for example, where there might not be ground-based alternatives. These are areas where space technologies really can come into their own. And of course, your individual mobile connectivity, that's something that you're all using all the time already, and that is only set to increase. What do we need from our networks in order to gain this kind of function? Well, we need global satellite networks and we need low-cost universal access. And I think it's really important for us to acknowledge that connection between cost and universal access. In some parts of the world that stand to benefit the most in terms of the provision of space-based services, these would be areas that don't have ground-based alternatives. It's really important that we include these areas within our vision for global networks. At this stage, it would be a real tragedy for global development if they were left out, simply because of the huge economic advantages that are going to come from this type of provision. So the final thing to say with this is lots of this ambition that we want from space-based services is fundamentally limited by the PV's power supply. So the things that we can do are mission capabilities. And so that's why we have a need for development. What are the current solutions? Well, currently 3.5 technologies dominate, and they have done so for the last decade or so, increasingly become dominant. This is partly because they provide the highest specific power, so that's watts per kilogram, and its efficiency and its mass that obviously feeds into that. They're also relatively radiation tolerant, so compared to other alternatives such as silicon, we get this high remaining factor that's comparing the beginning and end of life performance. And much in the same way as silicon is for terrestrial applications, 3.5 has this established record of reliability, which is hugely important in a risk-averse sector like space. You certainly can't have your expensive payloads being sent up and then the power system failing. And so 3.5 technologies really are the go-to for this. And to kind of highlight this, I'm showing you images here from 3 different types of launch, which went to very different environments. In the bottom here, we have the record-breaking 60 square meter panel that was on the Juno mission. This was a 3.5 technology that was powering the mission. Clearly going to an area of low illumination, but also very high radiation. So that was a very demanding type of environment. Then in the top right, we have TACSAT-4, which was actually developed by my former colleagues at NRL. This was an exploration mission for different types of orbits around Earth. This was looking at a highly elliptical orbit, which again is high radiation damage. And then finally, we have a little CubeSat here developed at the University of Surrey. This is quite an interesting mission because actually part of the objective was studying new types of technology for powering the system. So you can see just on the bottom there of the CubeSat, you've got a little cadmium telluride photovoltaic cell. So it was assessing how cadmium telluride might operate as a power system. But of course, the main payload, all of the communications and everything, is powered by 3.5. That's what you see coated on the sides of the CubeSat here. So despite these different satellites and exploration missions entering wildly different environments, the go-to technology that was used was the same. What was that? Well, it's the industry workhorse, the triple junction on germanium device, which is what you can see here. On the left is a triple junction device, meaning that different parts of the solar spectrum are absorbed in materials with different band gap. It belongs within the family of these relatively high efficiency cells. So on the NREL, that's the National Renewable Energy Lab chart of efficiencies, it's this kind of purple region up here where we have these very high performance cells. Now, NREL compiles this chart. It gets updated every few months when there are new data sets that come in, and it's something that we all like to refer to no matter what area of photovoltaics we're interested in. It's always fun to have a look at, but it actually has surprisingly little relevance very often to the practical realities of actually implementing solar cells in photovoltaic, in the actual conditions that they're going to operate in. So in this case, we have this device is very similar to these kind of record 40% plus type efficiencies, but in fact, the efficiencies that we see on orbit will be much, much lower, probably closer to 30%. The reason being that these are terrestrial spectrum efficiencies. The extraterrestrial spectrum has much more IR, and so it's a much less efficient energy conversion. These are also often characterized under concentration, which is generally not the case for space-based platforms. And also, we've got to bear in mind that this cell is actually not designed for peak efficiency. What it's designed for is longevity within the radiation environment, so maintaining a high but level efficiency for the lifetime of a mission. But this technology has been really, really highly enabling for many of the things that we use now for our space-based services. And you can see here in the bottom right, just a graphic showing some of the implementations just for this specific company, which is Solero. There are many other companies which provide comparable technologies. So it's a really huge number of different applications. However, it doesn't provide everything that we need in order to meet many of the up-and-coming challenges. What are those challenges? Well, we spoke about the need for next-generation satellite networks. And one of the things that these networks will face is radiation environments, challenging radiation environments. So when we talk about radiation environments for satellites, we are really most interested in radiation. This is electrons and protons which are trapped within Earth's Van Allen belts. So these are belts that extend out between about 1,000 to 6,000 kilometers from the Earth's surface, and then again from about 13,000 to 60,000 kilometers. Although those ranges do change depending on the specific latitude of the orbit. Now, one of the ways in which we can avoid these high radiation environment is actually going into a low Earth orbit, or which is also known as LEO. Now you can see a plot here in the top right, showing integral proton flux. This was compiled by my student Armin Bartel using data from SPENVIS, which is a European database of space radiation environments. You can see that the LEO environment is relatively low in terms of radiation exposure, which makes it quite attractive for many of these networks. And another reason why LEO is quite attractive is because it's relatively accessible. So this data here is for the first launch of satellites into the Starlink network, which many of you I'm sure will have heard of. It's been very popularized within the science pop press, and I think really rather captures the public imagination. It's also potentially a really enabling new capability that's being brought online here. However, it has some pretty significant problems as well. So they've selected to launch into low Earth orbit, and that has meant that actually they don't need to use 3.5 technologies at all. They can get away with silicon. So they've traded off the advantages of radiation tolerance of 3.5s in order to run on silicon, which is a lower cost platform. The problem with low Earth orbit that they will encounter is that you can't do everything that you would like to do with it. So you get very poor coverage at high latitudes. You can kind of see that in this illustration here of the network, where actually there's large parts of the globe that won't be covered, most importantly polar regions. So while I'm obviously sad for the people living in northern Canada who will not be able to use this service to download Netflix, it's also important to note this service is not going to provide us additional information in terms of polar region monitoring, which is unfortunate. Another thing to note about low Earth orbit is you've still got quite significant atmosphere there, so you need to have continuous adjustment in order to maintain orbit, and so that is using up propellant. Something that I think is clear from this diagram, I mean, I love it because it shows the real ambition of connecting up this network of hundreds of satellites, but we have limited space up there actually, and low Earth orbit is already very busy, and the higher you go in terms of latitude, the denser an array you need in terms of satellites for your continuous coverage. And so this really brings about the question of space junk. We are rapidly filling up this orbit, and that's going to become more and more the case. And so we need to question really the decision to operate in this regime. The concept of space junk also brings up a concern about security. So space junk can easily take out satellites through collisions, and also being in such a low orbit, so only a few hundred kilometers above the Earth's surface, these satellites are vulnerable to a ground-based hostile action. And if we are integrating them into some of the most secure parts of our information network, for example, connectivity between autonomous vehicles on our road networks of the future, we really need to make sure this network is secure. And there are definite question marks as to whether or not this type of orbit can provide that. There are alternatives, of course, and one that is really worth considering is a Molniya type orbit or a highly elliptical type orbit. This is quite desirable because it has a very long dwell time at very high altitude, which gives us excellent coverage at high latitudes and allows for continuous monitoring of polar regions. So for example, with Molniya, to monitor the poles, you could get away with just 2 satellites, whereas for a LEO type orbit, you would need 30+ satellites to do arguably not as good a job. So it's really advantageous in terms of coverage. You've also got way more space. I mean, just from a geometry perspective, you've got way more space out there than you do in low Earth orbit. So your space junk problem is a lot less of an issue. But one of the key challenges we have is that it's a much higher radiation environment. And you can see that on this chart here. Many orders of magnitude higher integral proton flux. So that's a key challenge to address. if we can develop technologies, power systems that can operate in this environment, then maybe we can start to actually launch satellites into this orbit and use them as part of our communications networks. One of the other challenges that I mentioned was space exploration in hostile environments. Well, it doesn't get much more exploratory or much more hostile than Europa. This is Jupiter's icy moon. What we would love to be able to do is land on the surface and drill beneath the thick icy crust to the liquid water ocean underneath and see what we can find there. This is one of the most compelling environments potentially for finding extraterrestrial life within our solar system. So it's really a very exciting area to explore. But it's also one of the most challenging environments in the whole solar system because of the radiation. It lies directly in Jupiter's high radiation belts, which are much more damaging than those of Earth. And you can see that shown here, again, using spin-based data, comparing electron and proton fluxes in the two environments. You're looking at many orders of magnitude increase within a Europa environment. And I think a good way to compare it or really frame the challenge is to look at the most recent Juno mission, the record-breaking 60 square meter panel that I showed you, that delivered around 500 watts, just shy of that. So all of those beautiful images and the spectroscopy and things that came back from that mission, that was all powered on less than a kettle. So pretty amazing feat of engineering. But one of the main ways in which they managed to achieve this was by using flyby missions. So they spent very short periods of time actually within high radiation environments and much longer periods of time in safe regions. And so that allowed them to acquire this data without the total destruction in a very short space of time of the power system. However, if we were to actually land on the surface of Europa, clearly we can't do that. We need to have a power system that is survivable continuously. And if you run the numbers and you say, well, I want to be there for a year and I want 500 watts, you're going to be looking at something like 12 millimeters of cover glass, which is enormously thick. That is what you would need to protect the sample. Protect the photovoltaic array. Cover glass is very dense. It actually has to be dense in order to protect against radiation. That's kind of the point. And so to meet this challenge, you need to launch about 1.5 metric tons of cover glass alone. So clearly that is not physically possible. It's beyond the regime that we can really consider. And so that really rules out this type of mission. We don't have a power system currently that can enable it. And so we're no longer saying, well, we just want to do things better. We want a power system to enable us to do things better. We're now saying we actually want a power system that's going to enable entirely new things that we currently can't do. So in terms of technologies that we're developing to actually pursue this ambition, what we're doing is looking at ultra-thin geometries. So radiation-induced defects degrade solar cell performance primarily by the introduction of defects which act as non-radiative recombination centers. And these reduce minority carrier diffusion length in the devices and ultimately then degrade the efficiency of energy conversion. Now, in ultra-thin geometries, we're actually relatively resistant to the presence of those defects because we can extract charge carriers before they recombine. And that's illustrated in the graph on the left here, where you see at the top your normalized short circuit current for 3 different device types, ranging from ultra thin at 80 nanometers through to much thicker devices at 3.5 microns. And you can see how their performance degrades as a function of proton fluence. However, the ultra thin device, we see a very flat profile, which is exactly what we want for space-based applications. If we look at the chart directly beneath, though, we can see one of the main design challenges we have with ultra-thin, which is in the 80 nanometers of material, you absorb very little light, even if you do have a good absorption coefficient. And what we really want to do is shift that line up so that we can get these good beginning of life and end of life performances. And when we look at the chart in the middle here, the external quantum efficiency, we can see how it really plummets in the case of slightly thicker devices, 80 nanometers, 800 nanometers, which is actually still very thin by modern standards. Whereas with the ultra thin 80 nanometers, we get almost no degradation in performance, but of course it's a lower performance cell to start with. Arguably, though, you could say even in this instance of a very low beginning of life performance, there could be situations where an ultra thin device would be preferable. So as I mentioned right at the start, your end of life performance is actually what limits what you can do in terms of payload. And so if you were going into very high radiation environments and you needed a long lifetime, there would be an argument to say, well, I can take that sacrifice at the beginning of life. What I need is sustained performance, because you can actually see that the 80 nanometer performance ultimately exceeds that of the thicker devices because of this effect. And it really starts to make sense when we measure the minority carrier diffusion lengths. With this kind of radiation exposure, we end up with minority carrier diffusion lengths that are around 100 nanometers. And so we really need to be looking at devices on that kind of length scale. So the first thing to think about when we're saying devices on this length scale, less than 100 nanometers, is how are we going to make a good diode on this kind of nanoscale? So just to give a perspective there on the orders of magnitude we're looking at, the our workhorse device that I showed you, the triple on germanium, that is maybe 6 to 10 microns thick. Some of the thinnest commercialized devices are maybe a micron. We are looking at an order of magnitude thinner again. So it's really beyond any regime that's currently studied in any depth. So can we create good diodes on this nanoscale? And there's loads of things that come into consideration. The first thing is we have an absolute ton of surface to contend with when we are looking at devices on this length scale. So we need to make sure we have excellent passivation. We also need to worry about contacting schemes. So we're only a few tens of nanometers away, separation between a metal contact and our active junction region. So diffusion of metals is a huge problem. So managing all that is very difficult. The person who's been taking on this challenge is my PhD student, Larkin Sayer. We have had a UK Space Agency program that was working on exactly this, where we collaborated with the epitaxy company IQE, and we're also funded by Isaac Newton Trust to look at this concept. So let's say we can manage to get around these technical challenges of creating a nanoscale diode. What about the light management system that we need for this? So clearly, we'd like to increase our absorption within that 80 nanometer film, and one of the best ways in which you can do that is with the integration of nanophotonic structure. And there are several different options for this. This is a project that my PhD student Eduardo Camarillo Bad and my PRA Phoebe Pierce have been working on. One of our most promising techniques that we've been looking at so far is displacement Talbot lithography. So the main challenge is that we can't use conventional contact lithography methods for this kind of patterning. We need features that are on the 500 nanometer length scale, and you simply you're diffraction limited in that regime. You can't image using contact methods. Displacement Talbot lithography is an emerging technique that's mainly been applied to LEDs at this point, so we're kind of borrowing from that knowledge that's been developed that actually takes advantage of the fact that diffraction is taking place, and of the fact that we actually are using a grid. So we have an array here that allows us to actually have a separation between the sample and a mask, and we actually use this Talbot effect of self-images at a fixed distance from the mask in order to pattern into a resist. And that's what we've done. So you can see here with the SEM images and the AFM here, the patterns are not 100% perfect, but they're pretty good, pretty uniform, and actually they cover a full wafer. So that's a 4-inch wafer there covered with nanophotonic pattern, which is a really exciting thing to be able to do, because ultimately that's the direction we need to be going in. So we've been working with the University of Bath on this. The displacement Talbot lithography tool is their tool. So I've got some results for you here, hot off the press. What does displacement Talbot lithography do to us? So do for us, do for our devices. This data set was acquired by Larkin just on Monday, so this is really very new. We can see what we have in terms of current voltage curve here for our on-wafer devices. By integrating that same device with the displacement lithography pattern, we get around a 50% bump in terms of our current density, and also really excitingly, a really nice improvement in terms of voltage, exceeding 1 volt VOC. So that's nice because this is a photo-generated voltage, right? And just to remind you, we are generating and sustaining that voltage just over 80 nanometers of film. So we're really pleased with this result. But there's lots of places to go with it still, right? Thinking about how can we design our devices better. One of the things that we've already got some preliminary results on is we suspect that we could do a lot better in terms of the design of the junction. So this is comparing our different doping levels. So this is a higher doping level, the type of doping that you generally would have with a thicker device. And actually by reducing down that doping, we can do a lot better in terms of voltage. And we may even consider moving towards a full heterojunction type device rather than a PN junction. One of the challenges, of course, with designing these devices is when we get to this nanoscale, many of the techniques we'd be familiar with using, such as drift diffusion simulations, they start to break down because quantum effects become much more important. So the effects of tunneling and interface effects. So it becomes more difficult to know for sure in advance of fabricating the devices what we're expecting. But we're working on our development of simulation processes to be much better at predicting that. So where are we going to take these devices? Well, we're certainly going to do the iterative improvement that we have. This is kind of the low-hanging fruit, really. With all the work that we've done, we're going to work on looking at those doping profiles, but also the integration of anti-reflection coatings. So these devices don't even have anti-reflection coatings on yet. They also have contacting schemes with around 10% coverage. Each one of these steps needs to be individually adapted and optimized to this new ultra-thin regime. We can't simply go straight to the end and say we want to optimize all these effects, because if you do that, inevitably it won't work and you won't know where it's gone wrong. So it's been an incremental process over the last couple of years since I came to Cambridge to get to this point. But as well as that iterative work, we're actually moving out in 2 directions. So one is towards the more fundamental and looking at smart design. So here you see a little snippet of some work that my student Eduardo is looking at. So can we design our grating to be a much better match to our cell and so give much better absorption enhancement? So this work, what you see here is absorption in the 80 nanometer gallium arsenide absorber region. You can see the solid line being rigorous coupled wave analysis simulation just for a single wavelength. And the question is, can we change our grating pitch in order to give a better match to the optical modes that are available with the waveguide that we've created there? The answer is definitely yes, we can, but it's a complex picture, right? So it's really dependent on features of the device, such as the specific materials that we're using and the thickness of those different layers. And there's a tendency, I would say, within this field of study to say, well, that's just a little bit too complicated to think about. So let's just put more nano in, and that's going to make it better. And of course, that doesn't necessarily make it better. So what we're trying to do is change the way of looking at it here. Actually, start from the design process and trying to be smart in the way that we design the optics for the cell. Moving in the other direction is looking towards space worthiness, right? So we designed these cells for space. We want to know how they're going to perform in space. And so we've got a Royal Society grant now to work with JAXA, that's Japanese Aerospace Exploration Agency. These are space flight engineers. Space worthiness is what they do. So they're going to take our beautiful cells and they're going to help us to destroy them in a really controlled fashion, hopefully, so that we can actually assess and really benchmark these for space, right? Have we developed a technology that's useful? And if so, what kind of environments is it useful for? So on the more fundamental side of things, one of the things that we're interested in is moving towards high efficiency. I mentioned that briefly as one of the key targets for space photovoltaics. Something that happens with ultra-thin geometries quite inherently is that we are absorbed, when we include some kind of light management structure, is that we're absorbing more photons in a thinner volume of material. So we end up with a higher charge carrier density for a given level of illumination. What that does is we will inherently see a local increase in our quasi-Fermi level splitting, and ultimately that can manifest as a higher voltage device. So with an ultra-thin geometry, you absolutely can break the single junction Shockley-Queisser limit because you break down some of the assumptions that actually go into calculating that limit. But in fact, you can go a little further and things can start to get really quite exciting. So when you get to a much higher regime of charge carrier density, the materials start to behave differently, and you can actually drive these materials. We've seen it for 3.5 materials already. You can drive these materials into a regime where they are highly non-equilibrium, right? So you start to saturate out the lower lying states in the band structure. You can saturate out cooling pathways, so restricting your interaction with electrons and phonons to maintain a hot carrier population. You can also park charge carriers in satellite valleys within the band structure. So you can do all sorts of interesting things in these high carrier density regimes. And I'm sure many colleagues will be familiar with this concept for investigating non-equilibrium effects in novel materials using ultra-fast spectroscopy. But actually, we know that we can generate those same charge carrier densities if we're smart about it with continuous illumination, particularly if we use things like quantum confined band structure to really force the carriers just into one space and to force them to stay there. What does this do? Well, by maintaining a hot or an energetic population of carriers that don't so readily dissipate their energy to the surrounding lattice, we potentially allow ourselves to obtain higher efficiencies. And in the ultimate case, a solar Carnot engine, which is what you see here. It's really the thermodynamic dream of photovoltaics. And it certainly is a dream at this point. It's a long way off, but the ultra-thin concept that we're developing is highly synergistic with the hot carrier concept because it's a regime which allows us to generate these really high charge carrier densities. And now that we have devices on this length scale, we certainly will be pushing them into these more and more extreme regimes and seeing how they perform, seeing how we can characterize the carrier dynamics. So I'd like to just take a brief, we've spoken about device fabrication quite a bit. I'd like to just take a brief moment to recognise some of the facilities that we have here in Cambridge and the essential nature of them really in performing this type of work. So for the development of the devices that we have, you need maybe 20 or so machines. Each different device process needs to be individually optimized for this regime. You can't say, well, I'm just going to take the process that I use for standard thick devices and I'm going to make a nanoscale device. I'm going to make my device 18 nanometers thick. You'd end up with something that didn't work at all if you did that. And so it really requires a lot of refining, a lot of patience, and that's where having our own clean room facilities really come into their own. So here you see my student Larkin working in the clean room. She's got some lovely IQE wafers there that she's about to fabricate into devices. But also when I'm talking about facilities, I'm not just talking about the equipment itself. It's of course the technicians that keep it up and running to a really high standard. And in this case, Melanie Tribble and Abby Lowe, who run the SP clean room, have been really vital in keeping these facilities going. So looking to the future as we're moving towards Ray Dolby Centre on the horizon and the potential of national facility, this is obviously a huge challenge in the way that we run our facilities, but also a tremendous opportunity to be much more connected in terms of the domestic network for processing, and also to expand our capability to allow us to really stay at the forefront of this type of device development. So the next area that I'd like to briefly discuss is talking about the synthesis of the materials that we're using. So 3,5 alloys, they are fabricated using epitaxial methods, and these methods are expensive, and we would like to reduce the usage down as much as possible. The ultra-thin geometries obviously gives a great opportunity to do that, 1,000 times reduction in materials usage, and with that, a corresponding reduction in machine time usage. However, one of the problems is that epitaxial materials use a substrate for growth, essentially is a template for the nucleation of the crystal, and the epitaxial layer forms a very strong bond with the surface of that substrate. So to remove the film, which we have to do if we're going to integrate it with a nanophotonic structure, to remove the film, we've got to break down those bonds, and generally that means a sacrificial etch process, and then if we want to reuse the wafer, a repolish. So it's a frustrating reality that even though we only want 100 nanometers of material, we may end up using, several tens of microns through this currently available lift-off process. So there's a real drive to develop new techniques that could enable wafer reuse and enable us to be much more efficient with our use of materials. And one of those is remote epitaxy. So that's essentially using a 2D layer which is positioned between a substrate and our epitaxial film. What that does is it allows the registry information from the underlying substrate to permeate through to the epitaxial film and allow that crystalline growth. But what you don't have is the bonding there between the film and the wafer. So in theory, you can then peel it away. You can just exfoliate it away, which would be great news, wouldn't it? That's the story. We've developed this at the wafer scale, and then we have a pristine surface for regrowth. Of course, that's probably not how it's going to work out. There's a lot more development that's required in order to achieve that. So the concept of remote epitaxy was first demonstrated back in 2017 from the Kim group out of MIT with a really groundbreaking work that they produced. This image you see here is actually from their 2019 follow-up paper, where you see a monolayer, interface layer on gallium arsenide, and then a bilayer. And here you have DFT calculations for the your potential fluctuation at the surface, and ultimately how that affects what you observe when you try to grow film, and that you can grow a monocrystalline film where you have a monolayer interface, but if you have a bilayer interface layer, it will be polycrystalline. So it's really extremely sensitive to that separation gap and the need for pristine surfaces. Unfortunately, it's simply not realistic to currently say, well, we're just going to transfer at the wafer scale monolayer graphene, which is going to be perfectly pristine and contamination free, and then we're going to exfoliate it and transfer it onto some other material, again in a way that is entirely damage free. So for that type of integration, there's a lot of development work that needs to be done. However, there's also other big payoffs from a material science perspective. So here we have the design space for 3,5 alloys. This shows band gap as a function of lattice constant, and there's potentially a continuum of different materials we could fabricate. However, very often we're limited to a few different lattice constants because of the availability of substrates. If we move away from certain lattice constants, what we end up with is the production of dislocations. That's what we see here in the bottom left with direct heteroepitaxy. However, with this kind of 2D interface layer or remote epitaxy technique, you don't form those strong bonds, right? So the nature of defect formation is going to be entirely different. And at this present time, it's really a wide open field with a lot of questions and very few answers. So it's an exciting place to be taking a look. And it's potentially something that could enable, as well as integration and cost reduction, it could also enable the development of novel low defect alloys. And with that, new device types. So what are we doing in terms of fabrication? Well, we're working on the large area transfer of pristine graphene. Can we do it at the wafer scale yet? No, but we maybe can do it at an area that's large enough to start to interrogate these films and start to develop the process. And we actually have some samples which are currently sitting in one of our MBE reactors, waiting for growth. And now we're back from lockdown. Of course, we're going to be moving full steam ahead with this, really trying to understand strain and defect formation. So the two people working on this are my PhD student, Mohammed Zulkarnain, who's also part of the Graphene CDT, and Lucy Goff, who is a PDRA in the Semiconductor Physics Group. So finally, I'd like to just make a quick note on innovation in epitaxy. So clearly compound semiconductors is a hugely established industry. It's worth 30 billion with a growth rate of around 20%. There's real leadership in the UK already with entities such as the Compound Semiconductor Cluster and also the IQE Mega Foundry in Newport. IQE is producing 10 billion wireless chips for smartphones annually, as well as other device types such as lasers for facial recognition, for example. So it's hugely established, and it certainly is a valid question to say, what are we doing in a research setting that needs to be done in this area? And to my mind, there's two key drivers of innovation: cost and integration. And clearly both of those are targeted by our space photovoltaics application, but it transcends space photovoltaics. Certainly one of the big applications here is the integration of 3-5 materials on silicon. And to do this, what we really need is new approaches, and so that's sub-TRL1 research, and that's the area where innovation in epitaxy and epitaxy development at the university research level can really thrive, and we're in a really well-established position here at the Cavendish in order to do that. So in conclusion, we have many applied challenges for space power systems, including next generation satellite networks and space exploration, but we need fundamental new concepts to actually feed into that. One of the things we're really focused on is ultra thin geometries, because they're able to target many of our key desirable items on our wish list. But really, that means also looking at things further back in the pipeline. So nanophotonic structure integration, non-equilibrium regimes of these alloys, as well as novel epitaxial techniques. So I'd just like to conclude by recognizing the contributions of others in this work. So the members of the Space PV group, if you'd like to follow what we're doing, you can check us out on the internet. We've also got other collaborators within Cambridge, within the Semiconductor Physics group, but also with the Hoffman group and the Joyce group in engineering. I'd like to also recognise our industry collaborators, IQE, and finally our collaborators of University of Bath and our funding agencies for sponsoring all this work and making it possible. So thank you very much for your attention, and I think we perhaps have another Q&A session to go to.